Let's now look at how we can differentiate the exponential function. Now I say the exponential function because I am referring to ones that have e as their base, not any other number. Now we've already seen that to just differentiate the most basic exponential function, e to the power of x, we get e to the power of x. So this one's very simple. But what happens if it's more complicated? Well, if we have a constant, it will just remain in the derivative. For example, differentiating 4 lots of e to the power of x still gives us 4 lots of e to the power of x. And that makes sense. After all, if you think back to when we differentiate something like x squared, we know that we bring the 2 down the front, and that gives us 2x. Having something like a 4 out the front of this just means that when we bring the 2 down the front, we need to multiply it by the 4. The 4 effectively stays there, doesn't it? And we get 8x. So the same thing happens here. The constant remains, and we just differentiate the part that has the x's in it. Now, using the chain rule to differentiate a more complex function, if we have something like y equals e to the power of, say, 2x plus 1, so we have a little function of x up here in the power. Well, the chain rule says, let's take the complicated part, the function of x, and let's call it something else, say u. So, in this example, if y equals e to the power of 2x plus 1, I can rewrite that as y equals e to the power of u, where I can define u as 2x plus 1. How does that help? Well, I can now differentiate y with respect to u. I'll do that right underneath. Now, if I'm differentiating e to the power of u, I'm going to get e to the power of u, just the same as I did when it was x. And if I differentiate u with respect to x, I just need to differentiate this part and I get 2. Now we can say that if we're trying to find dy dx, then we can take a shortcut and find dy du times du dx. And we know both of those. Dy du is here and du dx is here. Now as we go to write down dy du, we don't write e to the power of u. Why not? Well, because if we wrote e to the power of u, we'd end up with dy dx having some u's in it. And our original function didn't have any u's. We've sort of just added that in to help us out. So that when you come to write the u, don't write u, write down what u is, which is 2x plus 1. Now we need to multiply that whole thing by du dx, which is 2. Now, of course, the neat way to write that would be to put the 2 out the front and then write our exponential part. So we've got 2 lots of what we started with. Now, if we're looking for a shortcut, we can see that where did the 2 come from? Well, it came from differentiating the power. And what did we do with it? Well, we effectively brought it down the front and put it out the front as a constant. So we can use this little rule to make a shortcut. And let's write this shortcut down now. Once you've written down all of this, pause the video if you need to. Let's go a different colour. If y equals, now let's put a constant out the front and call it k. Let's write our exponential function and let's give it a function of x. Let's call it ax plus b because that's what we differentiated here. Then what we've found is that dy dx is equal to, well, we differentiated this part, which in this case would give us a, just like down here it gave us 2. And we brought that down the front. Now ours didn't have a constant, but if it did, we would have just multiplied our 2 by whatever that constant was. So we're going to bring the a down the front, multiply it by the k, so we'll get ak, and then we need to basically just rewrite the function that we were given in this part, e to the power of ax plus b. And this is a rule now that we can remember to use for questions like this. Now, this rule has a limitation. I'm not sure if you've spotted it, but it only works when the function of x up here is a very simple one. It's some x's plus or minus a constant. It wouldn't work if we had a much more complicated function up there. But what we've seen here with this basic pattern is we basically need to just differentiate what's in the power and bring it down the front. So a much better rule, and this is the one that's actually on your reference sheet for your exam, says if y is equal to e to the power of f of x, where f of x is just a function of x, then dy dx is equal to, now what do we need to do? Differentiate that function, so that gives us f dash x, and then we need to write out again everything that we were given in the original function. And this rule is in your reference sheet. It's a much better one than the one above because it allows you to differentiate anything that you can really that's up there in that power, bring it down the front, and away you go. It doesn't include a constant in this one, but I think we know how to deal with constants that are out the front. They will literally be multiplied by the derivative that you also bring out the front. So let's have a look at an example of one that's a little bit more complicated then, that allows us to use this second rule. If we have y equals, let's give it a constant this time, and let's give a more complicated function up here, x squared plus 4x, we can now differentiate that quite easily. We can say dy dx is equal to, now we need to keep out 3, so let's write that down again. We need to differentiate what's in the brackets, which in your head you should be able to see that this will give us 2x plus 4. We need to put that in brackets, don't we? Because that's one whole thing that needs to come down the front, complete. Then we need to just rewrite the rest of the exponential function. So we have e to the power of x squared plus 4x. And you can either leave it like that in the factorised form, or you could expand it out and have 6x plus 12, keeping that in brackets, so that that whole thing is then multiplied by the e. It's actually neatest as it is though. A few more examples now so that we can really practice. Each one of these has a little trick in it. This first one, the power actually has some brackets in there. So a good way to approach this one would be to begin by actually rewriting the function with the brackets expanded out. Half of 6 is 3, and half times negative x is minus 1/2 x. Okay, now I can easily differentiate what's in the brackets here and see that I'm going to get negative 1/2. I bring that down the front, so I'm ready now to differentiate. Dy dx equals, notice how I made it really clear when I was rearranging y and when I'm actually ready to differentiate and write dy dx. Now I'm bringing minus 1/2 down the front and multiplying it by the 4. If you want to do a whole extra line of work in there and tidy it up on the next line, I tend to just think this part through in my head because I know half of 4 is 2, it's got a negative on it. So I'm just going to go ahead and write down negative 2 at the front. But can you see where I got that from? I've taken minus 1/2 and I've multiplied it by the 4 that was already there. Now I need to rewrite the exponential part, e to the power of 3 minus 1/2 x. And you could write 3 minus 1/2 x, or you could even write half in brackets 6 minus x. Doesn't really matter. And we're finished. For the next one, the trick is that there's actually 2 terms here. Now, just as you can differentiate terms one at a time, when you have terms added and subtracted together, when you're dealing with non-exponential functions, you can do the same thing here. So just differentiate this part and then differentiate this part separately and write it all down. So we can differentiate it straight away. We need to differentiate what's up here and get 3, and that would bring a 3 down the front. Now there's 2 ways I could write this. I could give it a 3 and then rewrite everything that I was given like this, or I could think of this 2 down the bottom as sort of being almost like half out the front of e to the power of 3x. That's the same thing, isn't it? So whether I bring the 3 down, multiply it by the half that's already there, which gives me 1.5 or 3 halves, or whether I leave it written this way with the 2, it doesn't really matter. This 2 is basically a constant because it's a half, isn't it? I think this looks tidy, so I'll leave it this way. Now to differentiate the second one, up here I get 5 from differentiating the 5x, bring that down the front and multiply it by the 4, which gives me 20, and then rewrite the exponential part as it was given. For the third one, the trick is that the first term is an exponential function. The second term is just an ordinary function of x here without any e in it. The third part's got an e, and you need to be careful here you don't fall into a trap. What's the trap? Well, there aren't actually any x's in this part at all. So this part is just a constant. It's like if we tacked on plus 3 at the end, then to differentiate 3, you actually get nothing. So we can ignore that term completely when we're differentiating. But you need to be careful, look out for where the x's are. We're differentiating y with respect to x. And there's no need to pay respect to x in a term that doesn't have x in it. Okay, so the first one, we've got 3 multiplied by e to the power of 2x. Bring the 2 from your 2x out the front, multiply it by the 3 to make 6. Then we rewrite the e part, e to the power of 2x. For this next term, we've got a negative 5 already out the front. So the 2 comes down, multiplies by negative 5 to make minus 10. And with just an x, we drop down the power from 2 to 1. And then the last part is just a constant, so we'll ignore it and we're finished.